Okay, so one of the most useful applications of the density operator formalism uh, is the reduced density operator. Uh, it helps us describes the subsystem of a composite quantum system. So if you look at it in quantum mechanics, we have the density operator, let's say rho of x. That is more like the probability distribution over a random variable or one system. What would be rho xy? That's going to be like, so this is classical, this is quantum. So the if this was like the probability distribution over one random variable, one random variable, this is a joint probability distribution over two random variables. And if I need to calculate, I integrate out one of the variables, I get something called as the marginal. Usually that's the marginal distribution over just one of the random variables. So this is classically, what is the analogous operation quantum mechanically? So I have rho xy and I need an operator, a density operator or an operator that describes the statistics of all the measurements on one of the subsystems. So this map, or it can be the marginal, can be on the other thing also. I can analogously integrate out the y variable and get px marginal on another component. So this is all classical. This I do by something called as the reduced density operator. So let me by definition define it as the map that gives me the reduced density operator is called the partial trace map, partial trace over subsystem, one of the subsystems. So this is the reduced density operator, and trace of B is a map of operators known as the partial trace over system B. By definition, I define the partial trace by trace of B A1, A2. Let's say I have a by definition, the partial trace is I leave this guy as it is, and I have a trace operation B1, B2 on the system B. So A1 and A2 and B1 and B2 can be any vectors, in the set space of A and B respectively. And this boils down to, of course, by definition, the inner product. So this is the partial trace operation. Of course, we have defined it for a specific set of inputs which are a tensor product. This definition is complete by also recognizing that the partial trace operation, it's a linear map. So these two conditions, 1 and 2, the fact that it's a linear map, meaning it will act on any density matrix linearly. I'll trace out the system B. With these two properties, I can calculate the partial trace of any composite subsystem rho AB, whether in a tensor product form, or I can break down into a convex combinations, and I can take the partial trace of each of the constituents and do it. So this is so giving you a rough idea. Let's say I have a state which is a tensor product. Now the partial trace, just the operator, what is going to be the corresponding operator just on subsystem A is going to be tracing out the system B. I get rho trace of sigma equals to rho. So one more typical example would be, let's say I have a state as a Bell state. This is an entangled state, as we have seen. What's the Schmidt number? It's 2, right? This is an entangled state, and it has a density operator I can expand it out. If I trace out the second qubit, I get, if you calculate it, I'll get fill the missing steps. So I get I by 2. So note that this is a mixed state. And this is quite a remarkable result. I started with a pure state on a joint system. This was entangled state on a joint system. And I traced out one of the systems and I get the mixed state. In fact, I get the maximally mixed state. Where exactly on Bloch sphere this is? Well, this is going to be on the center of the Bloch sphere. That's I by 2. If I have 0 here, 1 here. And as we knew regarding the mixed states combine our subjective probabilities, subjective ignorance, with the quantum uncertainty over top of it. So that is in fact quite a remarkable result, that maximally mixed state means that in some sense I know nothing about the state. The state is exactly at the center of the block sphere. So I had the complete knowledge. It was a pure state for the joint system, and I am completely ignorant about the subsystem. This is a strange property that a joint state of a system can be completely known, yet a subsystem is in a mixed state. And that is one of the mysterious hallmarks of quantum entanglement or entangled states. I know everything about the joint system. In fact, it was a pure state. And I get a maximally mixed state of one of the subsystems. So I am completely ignorant about the constituents, both the constituents. Same will be with rho 2. That's also going to be this. So both rho 1 and rho 2 are at the center of the sphere. I know nothing about them, but I know everything about the joint state. It's going to be a pure state. So just as a passing comment, why the partial trace operator? What's so special about the partial trace operator that we have constructed? Remember, by definition, the partial trace operator was so one can in fact show that partial trace is a unique operation which gives rise to correct description of that gives rise to correct operations, correct description of observable quantities for subsystems of a composite system. So what does it mean? That means that let's say I have a joint density operator of two subsystems, and these are two in different corners of the universe. I'm just interested in describing an operator on just system A, which I make any observation, any measurements on subsystem A. I need a density matrix that captures all that. And that map is actually the partial trace map, and it can be shown that it is a unique map like that. So how am I going to show it? So I need a map on the joint system that gives the correct measurement statistics. So how does that map look like? So for example, let's say I have a measurement operator M. I have an observable, not a measurement operator. I have an observable M on system A. So what does that mean? That means that well, M will going to have some eigenvalues and eigenvectors. That's the spectral decomposition of M. Okay. So what would be a corresponding observable M tilde of the same measurement performed on the composite subsystem? Same what does it mean? It means if the system is prepared in, let's say this was the state of the system, and I perform m tilde. Upon performing m tilde, I should get the result m as eigenvalue corresponding to the projector of m tilde. The projector is this is the projector. That means I am doing something to system. This is a capital P. This is a projector on system A. I am doing nothing to system B. It's an identity operator. Once I apply this projector, I should recover back the eigenstate M, and I should get the eigenvalue M. So in fact, one can show through this logic that m tilde is nothing but just a decomposition, this guy, or in other words, this guy. That's the measurement, or that's the operator on the joint subsystem when I need a measurement of M on the system A. So this is a simple enough thing. Convince yourself this thing. So what do we need to show now? The next step is to show that partial trace procedure gives the correct measurement statistics for observation on part of a system. So suppose we make a measurement on system A described by the observable M. It should yield the correct measurement statistics. So like expectations values, so on and so forth. So what's going to be the expectation value of M on system A? This is going to be this. And that should correspond to, so this is sum operator rows of A. This is the expectation value of observable M just on system A. So both of these things are on system A, guys are on system A. And we demand that there exists some operator, we still don't know which one, row A, and the expectation value of observable M, any Hermitial observable on the subsystem A, that should be equals to the entire, the observable, corresponding observable on system AB, the joint system. Note that is just, it boils down to doing a projector on one of the subsystems, which is weird, and nothing on the second subsystem. And that is going to yield, remember this was the observable and this was the guy. So what observable or what density matrix operator row A on subsystem A is going to yield this guy, that when I perform a measurement of the same measurement on the composite system, this is going to yield me correct measurement statistics. This is the definition of what I require, that a measurement on the joint system, same measurement on the composite system, the joint system, gives me the same statistics as one done on the subsystem alone. So we can see, in fact, you should verify that partial trace indeed satisfies this. Partial trace operation, meaning if row A is this guy, then this indeed satisfies the above condition. Now, how does one show that partial trace is the unique operation or the only operation operation that satisfies this. So there are several ways of doing that, but just think about it. If I have a map row AB giving row, and let's say this map is not the partial trace, this map gives me some row A prime. So this is map 1, and my map 2 is the partial trace. That gives me row AB, row A, and for some other state, it gives me row A, row A prime. So on some density matrix, let me call it 1, 1, there exists a density matrix over which these two maps differ from each other. The partial trace map gives me row A prime, and this map gives me row A. Well, then I can straight away see that the trace of M row A is not going to be equals to trace of M, well, row A prime. Let me put this just as a subscript, row A prime M. And since this is true for any M, true for any M, I'll have differing measurement statistics. And since I've already proved that partial trace operation indeed satisfied this, partial trace operation indeed specifies this conjecture, I'll get a contradiction. So there exists some states over which the reduction to a single system was different, and partial trace was already satisfying the measurement statistics on one of the subsystems. My other map won't. So partial trace is a unique operation. The more formal way of seeing this is that we decompose the partial trace map. Let's say I have a map, not partial trace map, but let's say I have a map F, and I demand that that gives me the correct measurement statistics on system A. That's going to give me, there's some map row AB that gives me a density operator on the reduced subsystem. I demand that that map should satisfy this property, that the expectation value of M on the reduced subsystem should be equal to the expectation value of the same measurement on a composite system. Now, one can show that partial trace is such a unique map. How do I do that? I decompose. So show partial trace is unique. That F reduces to indeed partial trace. How do I do it? I decompose the map F using the Hilbert-Smith inner product. That's just decomposing a linear map into its constituents. That's just decomposing a linear map into some orthogonal components, where I define xy inner product to be trace of xy. So once I do that, what do I get? This guy is equivalent to some orthonormal basis of operators. Orthonormal normal basis of operators. So I decompose a linear map into its orthogonal, in terms of orthogonal basis of operators m sub I on system A, and this gives me nothing but this guy. So you can easily see by the same logic we saw that if there existed another map other than partial trace, it would differ from the partial trace operator on some input, and that's going to screw up my measurement statistic. Is the same way of saying that we know that the partial trace operation indeed satisfies this property. Okay, and we also know that this map is uniquely given by this decomposition. So this implies that f is, let me call this relation 1. F is uniquely determined by its orthonormal decomposition in terms of operators by 1. We also know that partial trace operation satisfies let me call it as 1 prime 1 prime. So this implies partial trace is indeed the unique function comparing 1 and 1 prime having this property. Thank you.